Start now. So, greetings everyone. Today we're going to be talking about writing tiny, stealthy, and reliable malware. So let's get a bit started about who am I? So I do offensive security at Ruptura InfoSec, and this consists of working on our internal C2 or writing ransomware or whatever payloads we need to work for our engagements. And in my spare time, I love most things low level. This includes hardware, assembly, and primarily C and C++. And obviously, your guess, this also ties in with writing malware and viruses. I love everything about them. I love reading stories about them, love reverse engineering them, and mainly I love writing them. And most importantly, something that's quite close to my heart is making blue teamers cry. When blue teamers pay £250,000 a year for an endpoint security solution, and we're able to walk through their network and their devices without getting caught, it's a great feeling. So let's go through the agenda of today's talk and what we're going to be covering. Firstly, we're going to be going through why you actually want to bother writing malware. What is it in it for you? And then we'll be going through what it takes to actually get set up and start writing malware on Windows. Then another important thing to have reliable malware is being able to subvert user land hooks. This will be quite a critical part of our talk, and we'll spend some time on that. Then we'll go through various ways in order to subvert static analysis, and we'll go through a few cool things such as import hashing, etc. And then we'll go through the next steps of where and what resources you could use to further better your malware development career. So motivations. Importantly, firstly, and most importantly is, I'll let everyone settle down quickly first. So, as I was saying, the most important thing is to have less detections. Being able to have less detections means that we can have an increased effectiveness for our campaigns, and this means that we can have more shells for a longer duration. And being able to act in the network for a longer duration lets us do cooler things and move around more. Another important thing is, as we've written the malware by ourselves, is that we can have better client feedback. We can give our clients potentially snippets of our source code so that they can better understand what actually the malware is doing and how it's able to abuse the systems. And another important thing is that we can learn something new. Hopefully by the end of this talk, you'll be able to learn something new too. So now let's move on to getting set up. What language do we want to do? Malware is just malicious software. So anything that is you can write software in, you can write malicious software in. However, we have a few constraints that we'll go through in the next talk. But for example, we've got quite a few languages such as assembly, but this isn't 1990s, and we don't really have the time to write malware from assembly by hand. Then we've got C and C++, which have been great languages. They've been around for about 50 years or a bit less. And they're a bit higher level than assembly, and they're great. Then you've got C#, which isn't really like C++ or C, and it's more something that Microsoft wrote for themselves. Then you've got some newer languages such as Rust, Golang, and Nim. Nim is just transpiled down to C++, and Rust and Golang are a bit bigger, newer languages. And you've got Python, which is an interpreted language, which is quite different. So when it comes to writing malware, you're going to have a few requirements. The first requirement we have is being smaller than 150 kilobytes. This might seem like a magic number I pulled out the air, but no, it's something that in the Vault 7 leaks by the CIA, they said ideally the malware should be under 150 kilobytes. This means that I will spend less time in the air and more time actually doing on the network. And then if you look at Rust and Golang, a simple hello world is 600 kilobytes in Rust and about 2 megabytes in Golang. This means that instantly too big and they got to get in the bin. Nim, it's a bit iffy because 70 kilobytes for a simple hello world, that gives us about 8 kilobytes of room to write malware in, which is a lot, but then that can quickly go over the 150 kilobyte limit. Ideally, C, about 11 kilobytes for a simple hello world, which is perfect. We've got a lot of room to work with, and it gives us the lowest level and the greatest level of flexibility. Then we want to have a language that gives us the ability to interact with the memory and invoke various Windows APIs. Having malware which isn't able to do this, or a language which isn't able to do this, makes our malware useless, and it's not even able to do anything malicious. And another critical thing is that we want to have no version-specific dependencies. For example, you don't want to rely on a certain version of .NET or a certain version of a specific DLL that's only available on an older or newer operating system version of Windows. And this allows us to maintain backwards compatibility. So a lot of you may have never written C before, and that's the language we're going to be going through with today's talk. So I just wanted to introduce a simple hello world so that you can understand it. At the top, we're just including a header file. This header file allows us to use various functions such as printf, and we're passing the hello world string to this function. And the main is the entry point of our code, the supposed entry point of our code, as you'll see. And we can see the size is around 10.5 kilobytes, but this changes depending on which Windows compiler you use. So looking at a bit more detail at this hello world, we can see that it's got an entropy of about 4.7. Entropy is quite important, as we'll come to see in later slides, and it's got various imports. You may be wondering, what's this VC runtime 140.dll? It's going to be an issue for us. As if you try running this binary on an older system, well, you're just going to get a pop-up saying, well, look, you can't run it because this DLL doesn't exist. Then we've got a bunch of sections in this executable section, and this executable, such as the text section and various other ones. The most important thing for us right now is the text section, which contains the executable instructions. If you want to have a play and do this by yourself, I published a script on GitHub, and it just requires PE file. So once you've imported that, once you've installed that with pip, you can have a go by yourself. So in our previous slide, we talked about entropy. So what exactly is entropy? It's a measure of randomness. How random are the bytes in your binary? And it's often used by EDRs and AVs as a static indicator. Some EDRs will use this for their machine learning, which is essentially just if statements, and they'll say if this binary's entropy is below or higher than a certain value, do some things. And often you'll find with packed malware, their entropy is higher than 7, and some people have come to me with solutions for fixing entropy by just concatenating the first chapter of Harry Potter. As you can see with Notepad from System32, it's got an entropy of around 6.5, which is a normal entropy, and it's good. But if you see Lockbit Black, which is a new ransomware sample that was recently produced by them, it's got an entropy of 7.28, which is higher than 7, and it's almost as an indicator that it's probably malicious. And we saw the VC runtime 140.dll in our previous slides. You may be wondering, what is that? So the CRT is essentially the C runtime library, and this will do a bunch of useful things for programs which compile with it. For example, it will set up the global SEH filter, it will call constructors, it will initialize global variables. And when our program actually enters, our main, what we said before, our main isn't called first. It first calls the WinCRT main, which will then call our thread entry point. So the first way to get around this dependency of having this VC runtime is by going into the configuration of your Visual Studio solution and selecting from multi-threaded DLL to multi-threaded. This, however, has some bad side effects. For example, first of all, your size is massive. We're at 138 kilobytes. It's about 120 kilobytes bigger. That's not good. So, and it also still is importing various functions from the kernel 32 and has quite a high entropy. So let's take a step back. Let's now try actually get rid of the CRT in a more suitable long-term solution, which doesn't increase the size. So first we want to tell the compiler, look, we don't want to use the WinCRT anymore. We want to go straight to our entry point. We can do this by saying a comment to the compiler, which tells it, look, use our entry point, not the WinCRT. And immediately our size is smaller and it's about 5.1 kilobytes. And we've got only 8 imports compared to the odd 70 or something imports. These imports are used to set up the global SEH filter, as you saw before. So this slide is quite overwhelming slide, but I'll try to go through each step individually. The first thing we want to do is disable C++ exceptions, as if we're not going to be linking to the CRT, there's no way we can actually use try-catch, as these are just wrapper functions for the SEH handling. As you saw before, we are linking to kernel 32. The way to get around this is that we want to ignore all the default libraries, so we're no longer linking to kernel 32. And then you'll get a little error saying unresolved security check. The way to get around this is that we then disable security checks, and then the compiler will tell us, oh no, SDL checks have been overwritten. For fullness, we'll just disable SDL checks. And the last step is optional. If you ever actually are writing malware and go through these stages, you'll probably, if you innately use memset, you'll get a little notification saying memset isn't defined. So you need to define your own intrinsic function, which overwrites the memset which the compiler knows. And when it gets around to that, hopefully this will be of use to you. So immediately, let's go through the cons of removing the CRT. Well, we've got no more try-catch C++ exceptions. We've also got no more SCH handling. This is quite inconvenient, but it's not the end of the world. As we no longer have a CRT which can manage all the C++ virtual functions, and we no longer have a virtual table, we can no longer use pure virtual functions, as there's no virtual table to look up against. And easy to use CRT functions such as string copy or memset or memcopy no longer available. And then it is possible to get C++ constructors and deconstructors working, but it's quite a pain, and simply, if you're writing malware, you don't really need object-oriented programming. It's not necessary for our goal. Another great thing is that we're going to have a lower entropy, and our file size is tiny now. We're about 2.6 kilobytes, which is a core of what we previously were. Now, to actually have a full hello world, I want to show you a way that you can do hello world without using the printf from the CRT. So we define a macro which takes a format string and a variable number of arguments at the top line. We can then allocate a buffer, format the buffer, and then write it to the console, and then free the respective buffer. The reason why you may be asking, why is it an if1 block statement, is because if you want to call this macro multiple times, well then the variable names will collide, so this way we don't get colliding variable names. And what's beautiful about this is that we can now correlate which import is being used where. As we previously were having a bunch of useless imports, we didn't know where they're being imported from. We can now correlate. For example, if we have write console, we can see where it's being imported from. This way, we can control what we're using. So when it comes to writing malware, you've got a bunch of other common functions. For example, if you're worried about malloc or free, well, malloc is just a wrapper for heap alloc, and the heap functions are just a wrapper for the virtual functions. The virtual functions are just wrappers for NT functions. As malware developers, we want to use something that gives us the greatest level of granularity and control. So why would you not just start at the bottom, NT allocate virtual memory, as this gives us the greatest level of control? If you don't believe me that some of these functions are just wrappers, you can open them up in a disassembler, and we can see that a free is just calling heap free with default arguments. If you're wondering where you can find some of the re-implementations of these various functions, such as string-related functions and whatnot, VX Underground have a great repository which has a bunch of useless re-implemented Windows functions, and another project I've been piggybacking off for a long time is UAC-me, and they've got a shared library which contains a lot of useful functions which I just like to use. So now we know about how to actually control our imports and have potentially a binary with no imports. Let's talk about how we can subvert hooks of EDRs. So why do EDRs even bother hooking the user land if they can just sit in the kernel and do everything from the kernel? So when EDRs are monitoring us, there are quite a few things they want to monitor. For example, they want to monitor what kind of network connection are we making, what kind of files are we opening, what kind of registries are we reading and writing to, and which processes, if our own or other processes, are we creating and allocating memory in. With kernel hooks, you've got a higher chance of instability because there's more chance for something to go wrong. And if there's something goes wrong in the kernel, well, you're just going to get a blue screen of death, and that's not great. Especially in a business environment, a blue screen in business, if you're causing denial of service, if EDR providers are causing denial of service for your customers, well, that's going to be a lawsuit on the way. And if you're in a kernel, you're going to have to be affirmative that this is a positive detection, and that means there will be more false negatives. And if a kernel EDR has to monitor all of that, that's really expensive, and time in the kernel is incredibly expensive. So it's a lot easier to go to just hook in the user land, and as it's a cheaper operation. So let's go through the creation of a process. When a process is created, this will just innately call entcreate user process, which essentially just verifies that it's the right image format. And in this case, we're only concerned with executables. So it's verifying that it's an executable. Then in the kernel, the address space for this process will be initialized. PB, the PB will be set up, and NTDLL will be mapped into this process. NTDLL is the first DLL that's mapped into every process. This is done at the kernel level. There's no way around it. That is a must. And EDRs can essentially register to various callbacks that will notify them on certain events. For example, on the creation of a process or the mapping of a various DLL or executable into memory, EDRs will be notified by this, and they can act correspondingly. So, for example, if they subscribe to PS set create process notify, when the initial thread of this new process is started, the EDR will be notified, and then the EDR can correspondingly inject various DLL into our process, which can then hook the various functions. As we can see here in an actual EDR, it loads the EDR DLL into our process. So, what is NTDLL? NTDLL consists of a lot of important things, such as native system calls, and this allows us to interact with files and memory and do a lot of other important things. It allows us to call syscalls. So, the life of a system call, at the start of every syscall, you will have move RCX into R10. The reason why it's doing this is because RCX is destroyed in the kernel space, and R10 is a register that's just not used. Then you've got move 18 into the EAX register. This is essentially just an argument, and 18 is quite an important number because these syscall numbers, an EDR has, if they're hooking our process, they have to hook on the 18 and hide the 18 from us. Then you've got a test byte pointer, and it's dereferencing this memory location against 1. So essentially it's just checking if it's a 32-bit operating system or it's Windows on Windows. And if it's a 32-bit operating system, it'll make the jump, and if it's not, it'll call syscall. And what into E is just a 32-bit way of entering kernel mode. So now let's look a bit at how EDRs may actually hook our program. So I was saying before, if we move EAX into 18, it has to hook on the first or second instruction. So as we can see in this specific EDR, it has a jump into another location in NTDLL. This is the E9. The E9 is just an opcode for a short jump. Then this jump goes to another jump, which is probably in the EDR DLL, and this also at the same time they'll save the stack and the registers in order to determine the nature of the call. And then once it's in the EDR DLL, they'll determine whether the nature of this function call, this syscall, is malicious or not. And then if the EDR determines that it's not malicious, they'll then restore the stack and the registers and move RCX into R10 and then move 18 back into EAX and then jump back to the test byte pointer where the program will continue. So as we can see, the EDRs have to hook on the first two lines of the code, and if they don't, well then they're just giving us away the syscall number, which is, if we have the syscall number, we can just call it ourselves. So now let's determine if a syscall is hooked. So as we saw below, 4C8BD1, B8. Though if we have those those opcodes, we can essentially determine if a syscall is hooked or not. Those opcodes are present in every syscall on Windows, because that same syscall stub is used for every syscall. If a syscall is hooked, however, the fourth byte, which is normally B8, it has now turned into E9, which is a jump. If we can determine if it's jumped, well then it's probably hooked. And we can do this with a simple memory comparison. As we can see, we get the address of whichever function we want, for example, NT-allocate virtual memory, and then we can then compare the address to our syscall stub, and then if it's not equal to 0, which means they don't match, we then determine that it is hooked, and then we can return true. If it does match, then we just return false, indicating it's not hooked. So now this isn't a great example, but let's look into how we can use compiler optimizations to our advantage. When we're using O1, which is favor size, we can see that it's calling memcomp and it's not actually optimizing this, which is quite weird. I found it was quite weird. However, if we are to use O2, which is to favor size, the memcomp's disappeared, and it actually does it actually compares the memory directly, and it aligns it, which is quite nice. If you want to have a play with this, I've provided a link to Godbolt, which is essentially a compiler explorer, so you can have a look yourself. So now we can change it. Instead of doing a memcomp, we can reproduce what the O2 version did, and essentially replicate it here. So if we want to do a memory comparison, we can just get the address, dereference it. A ulong is just the same as a D word, so we typecast it to that, and then dereference and compare against our memory stub. Because in memory, the B8, D1, 8B4C these bytes are the same. This is just a nice way to save a few bytes and avoid making a function call. So now, if, for example, we are talking about the .text section, which essentially contains the executable code, this will contain all the instructions in the NTDOL. And if an EDR hooks it, we can then determine that it's compromised. If it is compromised, we can see that instead of move EAX 18, we've now got to jump into another location. Now, if we want to unhook our NTDOL, which contains all the important functions, we want to think about how we can replace the text section. So we can just read the text section of a different of a location off disk or a known safe place, such as known DLLs, and just read it and replace the text section in our binary. So unhooking with known DLLs is we've seen the technique was first found by two great people, Modex and Jonas, who found it exclusively at different times. But there's some great people that have done great work regarding Windows, so I'd recommend following both of them. But essentially, the first thing we want to do is open the known DLL section object. This will return a pointer to us, and then we can map this pointer, iterate through the various sections in this pointer, in this DLL, and get the size of this text section and the virtual address of the text section in our process, and then set our text section for our NTDL to read-write executable. Previously, it's only read executable. The reason we're setting it to write is so we can overwrite it with the text section of the NTDLL we manually mapped. And once we've copied the memory, we can restore the permissions, and we've unhooked it. So now let's go into that in a bit more detail. So for this example, we'll just be using file test, which is a great tool to play around with files. So as you can see in the top left corner, we're opening a section handle to known DLL's NTDLL. We're then going to map this. As you can see, it works as we get a status success, and then we're going to want to map it with ntmap view of section. This maps it into our process memory, and if you are listening before, EDRs can also get a callback when processes map DLLs into their memory. However, I don't think any EDRs are currently detecting this, so you should be good for now. And then once we have mapped this, we can click Map Data Editor, and then we can see the infamous MZ header, which indicates that this is a portable executable. So now let's go through some code about how we can actually replace it. So the first thing we want to do is iterate through the various sections in our process and compare it to the .text, which is essentially the text section. What you're seeing at the top is we're ORing against OX202020 in order to lowercase it, and then we'll be comparing it to the to the text section in respect to little endian, the first 4 bytes of it. Once we've found the text section, we can then set the right memory protections on it, which is execute read write, as I was talking about before, and then we can copy the source, which is the known DLLs, into the destination, which is RDL or NTDLL, and then restore the memory permissions. We can then print a nice little helper message, which indicates that we've unhooked whichever DLL from known DLLs. So when we're doing this, there are various indicators of compromise which we need to be careful of. As I was talking about before, NT-map view of section has an EDR callback when we map a DLL into our process. And then NT-map view of section also might be hooked when we first initially call it. So an EDR might wonder, why are we opening and mapping a section handle of known DLL's NTDLL? We also might have the plain text string of known DLL's NTDLL in our process. And this is also quite bad. However, it's something that we can easily fix. And then when we set the memory protections of NTDLL, then we make them read-write executable. Having these three permissions is a clear indicator of compromise. However, this is only for a short duration in the time between copying the memory. Then we've also got an open handle to known DLL's NTDLL, and this is not something that normal processes do. And another IOC, if you're looking back in this slide, we saw status image not at base, and you can see that the address of in the data editor is in the 2s, and we can see here, yeah, we've got another NTDL in our process with different memory permissions. So this is we've got a few IOCs to worry about. So we've got if NT-map view of section is hooked, we can just use direct syscall, which is that we can store for example, the 18 number, but the respective syscall for NT-map view of section in our process, and call it directly. VX Underground posted a great white paper on that called Hellsgate, which I recommend checking out. I won't be diving into that too much, and there are also great blog posts out there. And yeah, as I was saying, an issue with this is that we now need to store the syscall numbers, or we need to dynamically resolve them. And if we're dynamically resolving them, then what's the point of just unhooking when we can just use the direct syscalls? And then for the known DLL's NTDLL static string, we can just XOR it or encrypt it with an AES key. If we're encrypting it with an AES key, then you've got an issue of a static key. So now we want to iterate through the loaded modules, because this gives us a lot more power. For example, if we wanted to unhook all the DLLs, even if they weren't hooked, so we just refresh all the text sections. So in the PB loader data structure, it contains a list entry. A list entry is essentially a doubly linked list which we can iterate through in order to see various information. So it's a common data structure the list entry is a common data structure that's used in the kernel. We can then iterate through in-memory order module list and then typecast backwards in order to gain access to the loader data table entry. And this gives us access to the DLL name and the DLL base, which is quite important for us. And there's a bunch of other information here. The reason why you see reserve is because these are structure definitions I pulled off MSDN, and Microsoft don't really like giving us full insight into what our process is done. But if you just search undocumented PB definitions or whatnot, you'll be able to find a reverse engineered version of this. So now we can iterate through the loaded modules. So the first thing we want to do is grab a handle to the PEB and get a handle to the head of the doubly linked list and the next entry. We can then iterate through this by pointing to the next value of the doubly linked list, and we can then just print out the name of the DLL and the address base. As you can see, we're using the print macro I was talking about earlier, and this, as you can see here at the bottom, I don't know if you can see, but we've got the C, which is actually CrowdStrike's DLL, and it's the last DLL loaded into our process. And you maybe, yeah, it's got a weird name, so let's move on. So, as I was talking about before, we can now iterate through all the DLLs and then unhook them all. So, we first try open a known DLL section handle to it, and if this works, well then it's probably a Windows DLL. If it doesn't work, then it's probably an EDR DLL, because EDRs can't hijack the known DLL section directory. Once we've opened a section handle, we can do what I was talking about before and just replace the text section. If we do this for all the DLLs, we're essentially refreshing them, and if there are any hooks in the text section, well, they'll no longer be there. So now, if we want to do this with a CrowdStrike, we can. Well, there is code for this. Don't worry. So we can see that we're able to unhook CrowdStrike. CrowdStrike, I've spoken to some guys there. They say they're able to detect unhooking for some scenarios, but for this, it doesn't seem to detect. And they may be able to scan the memory and see that it's been undetected, but that's very hypothetical, and I've never seen this being done in practice against various EDRs. So now we know how to unhook EDRs. Let's go through some various ways to get around static detections. So operation security, you need Opsec. Opsec is fundamental for malware. We essentially just don't want to open our mouth, which is what Opsec is. And this means we don't want to have static strings which contain, for example, our C2 IP or configuration information. So as I was saying before, yeah, we can get around static detections, prevent the disclosure of key critical information to our engagement. So if a reverse engineer just runs strings against our binary and they get an array of information, this is bad. We can also prevent import hashing. So I was talking about before, we can import a bunch of functions from various Windows DLLs. EDRs can and AVs can use import hashing in order to write signatures. For example, if we're importing various functions which are specific, so for example, if we're importing cryptography and file functions, an EDR may write an import hash rule which says this is probably ransomware. And another great thing is that we can slow down and raise the bar for static analysis. So we can use, what is API hashing? So essentially we can pass a string to a well-craft function, and this function will return essentially a number or like a specific hash for this string. So for example, this is the DJB2, which is a pretty popular hashing algorithm used by a lot of malware. And the 5381 is just a magic number which just seems to work with less collisions. So we can use hash string DJB2 and create a macro for this, so we can write hashes a lot quicker, so we don't have to retype code. To do this, we'll be using const expressions, which are compile time calculated values. So we stick this in front of our function, and then we define a hash which takes essentially a string, and we'll calculate the hash of this string. So by concatenating, so for example, if we wanted to hash NT-allocate virtual memory, we just write hash NT-allocate virtual memory. This will create the hash by under the name of hash NT-allocate virtual memory, and tokenize essentially just turns NT-allocate virtual memory into a string. This allows us to change the hashing algorithm quickly and change potential magic numbers. If you're interested in various hashing algorithms, OA Labs has actually presented a great database which contains a lot of implementations of various hashing algorithms. If you're also a reverse engineer, I highly recommend checking that out, as if you ever do come up against import hashing, I'll probably give you a good hand. So the previous example is where a lot of API hashing examples would just normally stop, and the implementations they provided were slow and not useful. So the first thing, if we wanted to have practical API hashing, we want to create two structures. The first structure is going to have a pointer to, it's going to have the hash value, and then the next one is going to have a pointer to the base address, which is like the DLL base of where the DLL is loaded in our process. So we can then create an array of this structure, and as I was talking about before, hash ntdll is just defined by this hash function, so we just pass ntdll to it, and then we just initialize the value of the address with a null pointer. So to have practical API hashing, we then want to populate this structure with the required DLL bases, and we can iterate through the loaded DLLs, as I was talking about in a few slides ago, uppercase the DLL names, because if you saw here, for example, that not all the DLLs have the same casing. For example, NTDLL is lowercase while kernel 32 is uppercase. It varies on various systems. So for For consistency and reliability, we'll uppercase them, and then we'll hash these strings, and then if the hash matches what's stored in this structure, we'll then store it, overwriting the null pointer. So the next step is, for example, we want to create a function to actually resolve the hash, returning the function address. So we'll create a function called getProcAddress hash. And this essentially takes a hash of the function we want to resolve and the hash of the module name. We can then iterate through the module hashes. If the hash exists, we then set the address, the base value to this, the module base. And if it doesn't exist, we'll just return null. And in this case, it'll probably just cause undefined behavior, as we'll try to call a null value. And then we can, all DLLs will have a bunch of exports. And these exports have a bunch of information related to these functions, such as the name, and the function base and the ordinal. And in these exports, we've got the number of names. So we're going to iterate through the DLL for the number of names and hash each and every name. If this name matches the specified function hash, we'll then resolve the function address and then return this address. So now, because I'm lazy, I like to make my malware development a lot more graceful and easier to do. So we'll define a simple macro which takes the DLL name and the function name. And this will essentially return to us and the address and actually dynamically call it. So for example, as we can see in the bottom image, that, for example, if we want to call entity-protect virtual memory, we just pass entity-DLL, which is the respective DLL this function is located in, and we dynamically, and it will be resolved. I then have hashfunc, which will then create the function hash with this function. It will create the hash of this, and then it will also create a type definition with the arguments passed. So entity status is what it will return in the top example, and handle and a p void are the two arguments. So it will create the required type def. So before, for example, if you wanted to create a simple calculator process, and this just pop a simple calculator shell with a create process, we can see that it will have two imports. These are imports that we know and control, and this is like with the CRT stuff we were talking about before. And if a reverse engineer was to throw this into a disassembler, they can quickly identify what the process is doing. And now if we're in to implement API hashing, and it quickly makes it a lot more complicated. And now we've also got no imports, which is fabulous, and we've also got a nice small size. So we're able to create a calculator process without having any imports with import hashing. However, one bad thing is we've got the plain text string, which is calc.exe, and someone just guessing, a simple guess would be right, and in guessing that this is just spawning a calculator shell. If you want to try this out, I've published the code for this specific example on GitHub. I do recommend checking it out. So now let's talk about stack strings. So for example, if you've got hello world, a quick, easy way to get around this is just creating an array and having these strings stored in arrays. So when they're used, they're just used as by being pushed onto the stack. For example, if we have a main function, and this main we've got two strings, hello world 0 and hello world with a new line. So we can see that the hello world is actually being used and stored as a global variable, while the string example is being used by being pushed onto the stack. And this is a lot better, as a simple string exe against our binary would not show this string that we just set up as a stack string. So now let's use some of the features of C++ in order to make our life as malware developers easier. So we can create a template which takes a type name, for example wchar or char, and the length of the string. We can then create a function that we calculated at compile time, and this will essentially go through the string and just XOR it against a key that we previously defined. And then during when we want to use it, we can just call deobfuscate against it, and this will just return the deobfuscated string. well, the deobfuscated string will be stored in mdata. So if you want to have random compile time keys, we can use the time compiler, the time variable, which is essentially just the time right now, and the compiler understands this, and we can just use this is just a random function I grabbed off GitHub, and we can just use this to generate random seeds, which I just use as a key between 0 and 256. So now if I wanted to make my life even easier, we can now implement this into macros. So we can define an off-w for wide character strings and an off-a for a CG. Because on Windows you've got wide character strings and a CG for backwards compatibility. So for example, our previous example of known DLL's NTDL, that static string, that we can now wrap in the macro of w, and this will essentially just XOR the string at compile time with a random key. And then when we want to use it, it will just decrypt it. So a simple strings against this will never actually show the known DLL string. If you're interested in string obfuscation, I highly recommend checking out these two repositories. Ad Obfuscator, that guy did a sick talk at Black Hat, and he's got an amazing white paper which goes with the talk, and a great repository which goes through a lot more features than what you can see here, and I highly recommend checking that out. So now I know you're all interested in some code, so on my GitHub I've shared a nice repository which hopefully you can go through, and I've documented all the code, and most things in this talk I've applied in this repository, and this will allow you to unhook all the DLLs, and yeah, as I was saying, it works with CrowdStrike, but CrowdStrike don't really detect it, but they're not meant to detect it, even though they say they are, but you know how EDR vendors get. And it's got a nice low entropy, and it's got no imports, so I highly do recommend checking it out. And it's commented well, so hopefully you do understand it. If you do have any questions, I'll be happy to answer. So let's go through some key takeaways. Unhooking is an easy task, and it's good, but it doesn't mean you're in the clear. For example, EDR vendors, while it is theoretical, they may, for example, place a few bytes at the start of the text section, which indicate when they hook it. And if they're scanning for these bytes, and since we've replaced the text section, it shows that it's been unhooked. Or there are various other ways to do this. Opsec can start to be achieved by obfuscating strings and import hashing in order to hide what we're actually doing, and I highly do recommend using these in your malware. And most importantly, keep it simple. Keep it super simple. The less you have is the less room there is for detection. Because if you start using a lot of code and copy pasting random code of GitHub into your project, you might actually just step on a signature and get detected. So going forward, if you enjoyed this talk, or you are interested in writing malware, the first thing I recommend you do, if you don't know C, is checking out the C programming language. This is a great book. It's only 263 pages, and it consists of it'll teach you how to write C. It's probably the best book if you've never written any code before to learn programming. Then if you want to learn a bit about reverse engineering, Dennis Yurichev has published an amazing book. It used to be free, now it's requires a $1 donation. And it teaches you different instruction architectures and how to reverse and various compiler optimizations. If you're interested in optimizing your code, Agner Fogg has a great 5-book series, which is absolutely mind-boggling, and I highly recommend checking it out. Now, if you want to learn programming on Windows, Pavel, he's got a great book, Windows 10 System Programming. He's also got a corresponding one for the kernel programming, and they both have an associated second part. If you're interested in Windows internals, there's the Windows Internal 7th edition part 1. I highly recommend at least reading chapters 1 through 3. The rest of the chapters aren't necessary, just read them as you need. And most importantly, VX Underground has a great malware repository, and they consist of great white papers. If you just read through all of it and just actually try it out, you'll get a lot further than most courses will take you. And that's it. Does anyone have any questions? Yeah. Does anyone have any questions? Yeah.
I enjoyed the talk.
Thank you.
So if you don't use the CRT and you don't really have any imports, doesn't that look suspicious from that point of view?
Yeah, sure, it looks suspicious, but then we can actually just choose to import various functions, like just use them uselessly, and they'll be imported correspondingly. So yeah, it does look suspicious, but it's better than having a lot more imports, which potentially could look more suspicious. So if we can have work from no imports and then build the ground up, it works a lot better. Yeah. Yeah. Potentially, but a lot of processes might map these DLLs. So, and I haven't seen. Yeah, it could, but I haven't seen it been done. Yeah. Yeah.
You had a slide for fine-based keys.
Yeah.
For encoding.
Yeah.
Wouldn't that change?
Yeah, the keys change every time you compile.
So how will it decrypt? So when you
because as you can see here, well, you can't see here, but key here is a global variable.
Yeah.
And this variable, here you can see the key is a global variable.
Yeah.
And so this is used by the decryption function here and the encryption function. So when you compile it, it's using the same key.
Yeah, but you're basically compiling it at 13 times, and you're generating the key, putting it in the malware, sending it over, somebody clicks on it. When you're generating it, the time's going to be different when somebody clicks on it.
But no, the key for the decryption is the same as the key for the encryption. Because it's a global, look, we're using the random seed. Yeah. This then stores, it will be moduloed against OXFF to get a value between 0 and 256. And then this is stored in the key variable. So the key value never changes after compile time. So the key here, for example, if this is 17 here, it will be OX17 here as well. So it doesn't get the time from the, when it's being decrypted. It gets it when it's being compiled. Any other questions? Yep.
I have a question about NoDL. The call for the anti-mafia section or graphic section, that's what triggers the kind of fallback. Later on in the load, the ball in the load from NoDL. You end up with, first being set up, but then at runtime, NoDL being agreed.
Yeah. Because I believe that when a process is created, the known DLLs is actually just a directory that allows you to load DLLs faster into the process. So yeah, any other questions? I'll leave it on this slide. Yeah. Thank you for coming.